Welcome back. This is the second part of my regression lecture for time series data. This lecture is going to cover model evaluation approaches. So how do I evaluate a regression model when I have time series data? So let me begin by asking you to watch some of my videos from the machine learning class. So this material is extremely similar to the material that I covered around penalized versus out of sample measures of fit in the machine learning class. So let me kind of summarize at a high level the distinction. So back in machine learning, I said there were two basic approaches to getting an honest evaluation of how well your model does. So by honest, I mean you're not using the training data to evaluate it, because that would be cheating. You might be capitalizing on chance because your model is optimized to make the errors small. So therefore, you need to do something to avoid that problem overfitting. So the two approaches are either add a penalty or use data that you haven't used to estimate the model. So the approaches for time series are basically the same. So use data that you haven't used to fit the model, or add a penalty that penalizes based on how complex the model is. So R makes this quite easy for you with the capital C, capital V function, and it reports 5 different measures. So the first is the predicted error sums of squares, which is leave one out cross-validation. So as a review, leave one out cross-validation is where you're using basically, I would have called it n-fold cross-validation back in machine learning. So you fit the model. If you have n data points, you would have to fit the model n times. Each time you leave out one case, having left out that case, you predict the left out case, and you tally up the errors on those left out cases across your n fits. So that's kind of the most extreme version of k-fold cross-validation. You could call it n-fold cross-validation if you want, or leave one out cross-validation. So this would be one of the out-of-sample approaches of evaluating the model error. Our forecasting library uses several penalized approaches. Some of these I went over in machine learning. So adjusted R squared adds a penalty for the number of parameters in your model, k. So that was covered in the basic regression in the machine learning class pretty thoroughly. AIC is another penalized approach where the penalty is 2 times the number of parameters. So 2 times the number of parameters plus whatever the some function of the objective function, SSE. And that's a slightly different penalty than adjusted R squared. The authors of our textbook recommend AIC. They also recommend another method, which is the bias-corrected version of AIC. Basically, AIC will often choose a model that's a little bit too big. Bias correction will correct for that. So you could be looking at this one as well. Another penalized measure that we often encounter is something called BIC, which is Schwarz's Bayesian information criteria. BIC uses a penalty that's a function of the log number of cases. So instead of just using a penalty of 2 times the number of parameters, it's the number of parameters times the log number of cases. And so as the sample size grows, the penalty is also going to grow with it. What I would recommend doing is just using the CV function and looking across them. And so often they tell you a similar story. When they don't, our author kind of prefers AICc, but also likes CV and AIC. I agree with the author on this. So let's go back to the previous example that I just did. So the previous example involved fitting this employment data either with 11 dummies, plus a trend and an intercept, or using various Fourier transforms with different numbers of terms. And so then the question is, which of these should I use? So what you'll see is that I've used it for the model with seasonal dummies. Then this is going to be the version with just k equal to 1. So k equal to 1, meaning I have a sine and a cosine term, a slope and an intercept with a total of four parameters. This would be 2 Fourier terms, 3 Fourier terms, 4, and 5. And so what we want to do is look across the CV values. And so if we use dummies, our cross-validated error sums of squares is about 29. 29 point, call it 0.3, 29.3. If I only have one Fourier term, you can see the errors are substantially worse. If I go out to 2 Fourier terms, I do about the same, but with far fewer degrees of freedom. If I take 3 Fourier terms, you can see I actually beat the dummies, and I do the same if I have 4 Fourier terms, although the decrease is getting less. By the time I go out to 5 Fourier terms, what you'll see is that errors are getting worse. So I'm probably overfitting at that point. If we were to use AIC, we see a pretty similar story. So 200.7 with all the dummies. When we start using Fourier terms, 1 isn't enough, 2's better, 3's better yet, maybe 4 is even better yet, but not by much. And then if I go out to 5, it starts to increase. So I've overfitted. I'm starting to overfit there. If you use the adjusted one, what you'll see is that we actually prefer a more parsimonious model, so just using the 3 Fourier terms. And if we used adjusted R squared, what you'll see is we come to the same conclusion as we do with AICc. So I may be inclined to use a little bit more parsimonious model and would probably choose the 3. I just don't get much of an improvement by going beyond that. I'm probably starting to overfit, so I'd be a little bit conservative on that. So that's how we use these fit statistics. The last example that I want to go over with you in this module on time series regression is to illustrate the spline command. So I'm going to do this using the T-bill data. And so there's a function in the forecast library called splines that's going to give us a natural spline. So remember what a natural spline is? Natural spline is going to be a cubic spline that extrapolates with a linear function. So extrapolation is very questionable with these non-parametric methods. Natural splines avoid that by just fitting a linear trend beyond the end of the time series. So what I've done is to create a plot with the original data, the observed data, and the fitted spline model. And so the spline you're going to see beyond the end of the data is a line, the slight upward trend. And what I'd like you to note is how wide the prediction intervals are. And that's because we're actually using a fair number of degrees of freedom with the spline model. And so the forecasts are not that reliable. Now, let's go back to a plot that I made during the previous module where I just used the naive method. And so what you're going to see is that the naive method gives much more reliable forecasts than the splines. So when I look at the 95% prediction intervals, they range from about -5 to maybe +8 or 9, 7 or 8. whereas the prediction intervals for the spline were much wider. So ordinarily I love splines, but here would be a case where I would say the naive method is preferred over the spline method because the prediction intervals are tighter. Okay, so that's it for the regression module.